Oh, sorry.
Okay, awesome. All right. Our next speaker is Abby Derrico. And Abby grew up in Lancaster, Pennsylvania, and attended Temple University in North Philadelphia, where they studied physics and did their undergraduate research in experimental materials science by Professor Alexander Gray. Now, Abby is a PhD student in physics and doing their thesis research focused on sustainable fuel production and pollution degradation by Professor P-Dong Yang. Abby is also a proud organizer for the Graduate Student Union, UAW 4811. Excellent. A weekly volunteer at the Berkeley Food Network, and a soprano in the UC Alumni Choir. They enjoy swimming in the Berkeley Marina, losing at poker, and watching television. So please.
So, thank you so much. I think this mic is just for you guys, yeah? So I can move around a lot. I'll talk loud, but holler, and I'll take it with me if I need to, okay? Thank you for that great introduction. Thank you guys for having me and for being here. I'm Abby. I'm a third-year physics PhD student in the P-Dong Yang group, which is a group in chemistry. I really liked the beginning of Sophie's talk. I could also be described as a self-made chemist. I did not have any experience in that in undergrad. I have been learning in my PhD and having a lot of fun with it. And I'm here today to talk about plasmonic catalysis, or how plasmonic nanoparticles use light to break chemical bonds. And I'm going to spend most of my talk just trying to explain what I mean by plasmonic catalysis to hopefully convince you that it's a really powerful tool. But a really powerful tool for what is kind of the thing I want you to keep in mind. So my motivation for this project is thinking about per and polyfluoroalkyl substances. You might have heard about these. They're a family of synthetic chemicals that build up in humans and are linked to many health problems, including cancer. They're found in things like nonstick cookware, dental floss, and firefighting foam. And they have these really strong carbon-fluorine bonds all over, which make them very resistant to degradation. So they never break down in the environment. And I hope that I will be able to use plasmonic catalysis for PFAS degradation. So keep that in mind. That's why we care about plasmonic catalysis today. So with that, what is plasmonics? Plasmonics is the study of plasmons in metal structures, metallic structures. Plasmon is a unit of plasma oscillation. You might have heard about plasma. It's the fourth state of matter, so it's not a gas, a liquid, or a solid. It's something different. It's characterized by free electrons. Some types of plasmas that you might encounter in your day-to-day are things like lightning and also the sun. And the thing to think about here is that electrons have charge. And so when you have a state of matter that consists of charged particles, there's a lot more interaction between the particles than with our other three stages of matter. So in a gas, your gas molecules that are bouncing around in the air, this molecule moving over here doesn't impact this other molecule unless it bumps into it. But electrons move at all, and they impact each other because of their charge. And so that leads to a lot of collective behavior that kind of defines the plasma as a state of matter. That's what makes it so unique. Yep. Plasmas, what is oscillation? Oscillation is a really fundamental concept in physics. We run into it all the time. And it's very simple. Something like a mass on a spring or a mass on a pendulum is like the quintessential example of an oscillator. And every time you run into something that oscillates, it basically behaves exactly like a spring, and you can just think about springs. So as I said, we're thinking about PFAS molecules and how we can break these bonds. And the thing that I think is kind of the most important part of this plasmonic catalysis picture is the idea of an oscillating plasma. So I'm going to spend a little bit of time talking to you about how we get a plasma to oscillate, because I think it's really important and valuable. So first off, I told you about some kinds of plasma like lightning and the sun, but I actually don't care about those at all. What I care about is the plasma of electrons in conductive metals. So electricity is the flow of electrons. So if you have a metal that can conduct electricity really well, that's because the electrons in it are free to flow within the entire bulk of the metal. They're not trapped to one atom or another atom. And so the electrons in that metal form a sort of a plasma, an electron plasma. And we also know that these electrons have a negative charge, so they can be pulled by electric fields. So imagine for a second that you have a hunk of metal and you apply an electric field, it's going to tug on this electron cloud and pull those electrons away from the positive bulk of the metal, leaving behind the atom centers that have protons that are positively charged. So now you have a negative thing and a positive thing that are a little bit separated, and we know that those charges attract each other. So what's going to happen when we turn off our electric field? Those negative electron clouds are going to be pulled back toward the positive bulk of the metal, but it's not going to like snap right back into its original position. It's going to bounce around a little bit. It's going to oscillate, just like a spring. So this is our oscillating plasma. But there's actually a lot of different types of oscillation. When we turn on and then we turn off our electric field, our electron oscillator is going to start moving but quickly dampen, just like this spring that we look at here. So it starts moving and then it slows down fast. But you can imagine if we turn our field on and off, or better yet, we point it in one direction and then the opposite direction over and over again, we could drive the oscillator, increasing the size of the oscillations over time. You could imagine pushing your kid on the swings. You push the kid once, they swing a little bit, then they slow down and stop. But usually keep pushing them over and over again until they fly higher and higher, having a great time. But we also know from pushing your kid on the swing, you have to be careful to do it at the right frequency. So you can't just push at arbitrary intervals. You want to push in pace with the swing itself. So we talk about the right frequency. The frequency is just the number of oscillations in a given amount of time. So we know we care about these plasma oscillators. We want to get them going. We want to drive these oscillations to be strong. But how do we know what frequency we're supposed to be pushing at? For a spring, the frequency of oscillation is determined by the stiffness of a spring. But for our electron oscillator, the frequency is determined by the strength of the pull between the negative electrons and the positive bulk of the metal, which mostly depends on the density of electrons in the metal. So you can imagine if you have two different metals, one that has a bunch of conduction electrons for each metal center, and one that has fewer. If I pull all of these electrons off to the side, the force between them and the metal bulk is going to be pretty strong because I've displaced a lot of charge. But over here, it's going to be less strong. There's less electrons. And so different types of metals that you interact with have different amounts of free electrons in them. Aluminum has about 3 conduction electrons for each metal center. So there's a strong pull and a high frequency of oscillation. Those electrons are going to oscillate fast. Gold, on the other hand, has only 1 conduction electron per metal center. So you have a weaker pull and a lower, slower frequency of oscillation. So now, we've got almost all the pieces, but how do we match? Oh, sorry, go ahead. Please.
On the previous diagram, does the number of, does the density of electrons correlate with the goodness of conducting material?
Yeah, this is a really good question. I was showing these slides to a friend of mine who is a physicist, and they asked me that same question, and I said, I don't know. I mean, no is the answer, and it's actually why I picked these 2 metals. So the first reason I picked them is that, I'm trying to tell you about the density of electrons, but people often think about mass density, right? And we know that aluminum is really light and gold is really heavy. So they actually have the opposite mass densities compared to these charge densities. So that's one thing to note. But the same is kind of true of their conduction. Gold is a really good conductor and aluminum is not. And so what does that have to do with the free electrons? I did look it up to find out the answer. The answer in this case that I can tell you is that this is a pretty simple picture and it works well enough for our plasma oscillator, but it does not work very well to describe a lot of other electric phenomena in metals. That stuff can get really complicated. There's also a lot else going on that, again, we don't care about for the purposes of our plasma oscillator, but matter a lot for things like conduction, which is these different metal centers have different numbers of protons and neutrons. They have different electron orbitals in different configurations. So all the rest of the electrons that aren't free are doing other stuff. That might make it worse for conduction. But it's a really good question. Maybe you and I should Google it afterwards. Sorry, I didn't go on ahead of time. Other questions here? Okay, cool. So we know how to find the right frequency, but how are we going to match it? How do we turn on and off our electric field at the right frequency? Well, lucky for us, it turns out that light already contains an oscillating electric field that points in one direction and then points in the other direction over and over again. And the frequency of a light wave depends on the color of the light. And so we can tune the color of our light to match the exact oscillating frequency of our plasma oscillator and drive it with a specific color of light, just like that screen. So this is the picture of how we're going to get our plasma oscillator going. So we'll put a pause on this for the moment. I'm going to talk about catalysis, and then we will come back and bring our plasmons in later. So catalysis is a chemistry concept. It's a modification, but especially an increase in the rate of a chemical reaction due to an added substance known as a catalyst. You can think of the classic backyard chemistry experiment of the Mentos and Diet Coke. You kind of know that in the Diet Coke are all of the things that you need to make a bunch of bubbles, but you can't get it to make as many bubbles as you can when you put some Mentos in there. So the Mentos are doing something to help the reaction go a lot faster, but they don't kind of contain any of the reactants of the reactions. And so a lot of scientists work to design catalysts for otherwise inefficient chemical reactions. This is one thing that my group, led by Professor Pei Yang, has been studying for more than 20 years. And I think it's instructive to talk a little bit about the types of catalysts that you can work with. One of the big divisions is between heterogeneous and homogeneous catalysts. Heterogeneous catalysts are where your catalyst is a different phase from the chemistry that's happening. So this is like your Diet Coke and Mentos. You're putting a solid catalyst into your liquid chemistry. Homogeneous catalysts are the same phase. So a liquid catalyst in your liquid chemistry. An example of that is industrial processes for making acetic acid, which is like the thing that's in vinegar. Use liquid metal, dissolved metal ions to catalyze those reactions like rhodium and iridium. So that's an example of homogeneous catalysis. You can also have different types of materials that use as catalysts. Inorganic metals catalyze a whole ton of different reactions, but there are also some organic catalysts like polymers, or vitamin B in your body acts as a catalyst to form carbon-carbon bonds. And my lab works primarily with heterogeneous metal nanoparticle catalysts, which can catalyze a wide variety of reactions. In our lab, we'll study things like the carbon dioxide production reaction, which can convert CO2 into more valuable fuels and chemicals, the glycerol oxidation reaction, which breaks carbon-carbon bonds in glycerol to form more valuable chemicals, or the hydrogen evolution reaction, the classic water splitting, which forms clean hydrogen. Yeah.
Where is the line between heterogeneous suspended nanoparticles and homogeneous liquid phase?
Yeah, so the difference is in like the chemistry at the atomic level. So the nanoparticles that we use are solids. They're metals in a lattice, like this picture that I showed you. This is like the defining difference between a solid and a liquid, is that in a solid, you have like lattice structure like this. And you don't have that in liquid. You have like a metal atom that's surrounded by some water in solution. And so that's the difference, is you're dissolving the metal itself into solution. And you can see that kind of stuff in the lab. Like you put the metal in there and it starts out solid and you can see it and it's cloudy, and then you like shake it for a while, you know, you stir it, and then it turns clear. And so you know that like something fundamentally has changed. You've dissolved it, just like salt or sugar in the kitchen. Okay, so my lab uses heterogeneous metal nanoparticle catalysts. I hope I've convinced you that heterogeneous metal catalysts are a good category to be working in. There's a lot of stuff there, but why nanoparticle catalysts? The biggest reason is that high surface area can increase catalytic activity. So you can see that this is kind of like a quintessentially heterogeneous catalysis thing, right? So you have your hunk of metal and you throw it in some liquid, and only the outside of that metal can participate in the chemistry. And so if you break up that metal into a bunch of different pieces, that gives you more surface area to work with. But there's other ways that we can engineer nanoparticles specifically to sort of tune their properties and have them participate in chemistry in exactly the way that we want them to. So one of these ways is that different nanoparticle shapes can have different exposed crystal facets. A facet is like a slice of a crystalline material. You could think of a layer cake, you know, if you slice it the regular way, you'll expose some stripes of cake and frosting, but if you slice it parallel to the table, you could get just icing or just cake. And so just in that same way, when we slice our crystals in different ways, we're exposing different atoms in different arrangements, and those are going to participate in our chemistry in a different way. And we can do this by changing the shape of our nanoparticle. Different nanoparticles can also have different types of surface atoms. And the key thing here is just that surface atoms that are like more isolated with fewer neighbors actually tend to be really good for catalysis. And so we like these adatoms that land on the surface, or step atoms and kink atoms. And so our smaller surface area nanoparticles already host a lot more of those than like a bulk metal. Plus, we can engineer them specifically to have a lot of these features. Yeah.
So it's really basic.
Yes.
Nanoparticles. Is this something that has been created into recent manufacturing processes, or are nanoparticles something that had existed before very long?
Yeah, great question. So there's a ton of different ways that you can make nanoparticles, and so some of them are a lot more recent from sort of industrial processes. So you can imagine people are always talking about lasers and like I don't know, I haven't done any of this, but I kind of imagine that it's similar to the tools that people use in all of these micro fabrications. You can like use a mask on top of a bulk like metal.
Did Neanderthal have problems with PFAS?
Well, that's a different question. I'll answer both of those. So we have some more modern nanoparticle techniques like etching with a mask that are very recent. The techniques that I use are colloidal synthesis techniques. So you can just mix some metals in solution in a certain way, and then they precipitate out of solution and form solid metal nanoparticles that are like floating in a liquid. But there's actually a really interesting example of some old, actually plasmonic nanoparticles in this artifact called the Lycurgus cup, which is a like metal. I think it's a glass cup, but it's got some metal nanoparticles in it, and they have some optical effects. So we've been talking about light exciting these plasmons, right? And so, what's the simplest way to think about this? They absorb very strongly at the right color of light that sets the plasma oscillator going. And so this cup, depending on whether you illuminate it from the inside or from the outside, looks like a different color. And that's how we figured out that there were nanoparticles in it. We're like, what's going on with this cup in the light? They don't know where those came from. Maybe it was like some accident of their manufacturing process. Maybe it was kind of on purpose. But that, as far as I know, is the oldest nanoparticles. PFAS are from modern industrial processes. They are not nanoparticle, just a specific type of molecule that we engineered in recent history to do what we thought were useful things, like non-stick cookware and firefighting foam, but have had a host of negative effects. Other questions here? Okay, so I joined this lab where we're doing a lot of heterogeneous metal nanoparticle catalysis, but this still doesn't really answer, why are we getting plasmons involved in this? Now, there's a couple of reasons that it's easy to get plasmons involved. We're working with metal nanoparticles already. They already host plasmons. I didn't have to make any changes. All you have to do is shine some light, and you can get that plasma oscillator going. But the biggest reason is that all that energy that we're imparting from our light has to go somewhere. So we've learned how to transfer energy from light into these electrons to get them oscillating. But what happens next is that actually we generate some hot carriers. So we call this plasmon decay. After you excite the plasmon, where does that energy go? It decays and can produce hot carriers, which are excited electrons, and then also the positive space that they left behind, which we call an excited pole. And these are kind of the important thing that we're excited about. But also, the hot carriers relax by the electrons colliding with one another. And so this redistributes the energy from a few excited electrons to many electrons. And then those electrons redistribute the energy back into the metal lattice itself, causing it to heat up in a process called thermal relaxation. But again, what we really care about are these hot carriers. So we know now how to set off our plasma oscillator. And it turns out that when you do that, you can generate some excited electrons. So what? We talked a little bit earlier, but we know that many molecules are joined by covalent bonds where two atoms share electrons. And these covalent bonds form because it's energetically favorable for them to do so. So if you have hydrogen and chlorine, and they share 2 electrons to become hydrogen chloride. This happens because our product, hydrogen chloride, is more stable than hydrogen or chlorine on their own. But if you add an extra energetic electron to this picture, like the one produced by a plasmon decay, it can actually break that covalent bond by making it no longer energetically favorable for hydrogen chloride to exist. So that, of course, brings us back to our PFAS molecules, where we have strong carbon-fluorine bonds that we're interested in breaking. And so that brings us to our picture for PFAS degradation. First off, there's some theoretical evidence that gold nanoparticles can be used for exactly this sort of plasmonic PFAS degradation, where you can excite a plasmon, get your electron oscillator going, and then that energy decays, produces hot carriers, and they can be transferred to those carbon-fluorine bonds and break them. Also, some other metals have shown evidence for acting like catalysts for PFAS hydrodefluorination, which is the same reaction. It's the breaking of the CF bond. Metals like platinum and palladium. And so we can try to decorate these catalytic metals onto the surface of our plasmonic nanoparticles in something known as an antenna reactor system. So you can imagine if this is like your gold nanoparticle that you hope will produce these hot electrons, and you have some catalyst reactor like platinum or palladium. There's all sorts of different ways that you could decorate this reactor catalyst onto your antenna, and then you can excite a plasmon and try to funnel those hot electrons from the gold into your palladium or platinum right to where that PFAS is hanging out and hopefully breaking down. So this is the picture for the research that I hope to do for the next couple of years, but I wanted to show you some of the data that I have today. This is a picture of my gold nanoparticles that I've tried decorating with some copper nanoparticles. Those are the smaller ones that you can see in like a nice layer on top. And I can do some absorption measurements of these nanoparticles where I'm literally just shining light at a bunch of different frequencies through the catalyst and then measuring how much light makes it through to the other side so I can calculate how much light was absorbed by the catalyst. And as we talked about earlier, from the great question, the light that is strongly absorbed at a certain frequency, that's going to be the same frequency that sets off our plasma oscillator. And so,
excuse me. What is the medium where that picture is being taken?
This is from a scanning electron microscope. So this is actually on a different electrode, a solid one that you couldn't shine light through. It's made of carbon. But then I do the same deposition on some glass slides. And so glass, like catalysts on glass slides are hard to image, but you could imagine that it looks exactly like that when we shine the light through it. So this is our spectra for gold. You can see the big absorption peak right here at about 535 nanometers. That's the well-known plasmon peak for gold. So we see that the gold absorption peak's at the same frequency that's going to drive those plasmon oscillations. Copper also hosts a plasmon, but we care about that one less because it's not as good. And then we see that even when we decorate our gold with copper, we still see the gold plasmon peak, maybe shifted a little bit. And so what this tells me is that I can buy an LED at around 558 nanometers, which is like a yellowish green, shine it on my gold nanoparticles, and I'm going to set off some plasmons. I'm going to get those plasmon oscillators going and hopefully producing hot electrons.
When you said on that last slide, you have the gold band and copper and copper decorated, gold decorated copper. You said that the copper was less useful. Can you just explain for them why that's less useful?
Yeah, there's two easy reasons when we're talking about doing plasmonic catalysis. The first one, and probably the biggest one, is that copper is more prone to oxidation. And when copper oxidizes, it forms not a metal. So it's no longer conductive and also can no longer host plasmons. So even if you just get a copper oxide shell on your nanoparticle, it's not going to be as plasmonically active. It's also less stable when you're doing catalysis. The copper atoms tend to migrate, which can be really good for forming those things we were talking about earlier, like a lot of atoms that are sort of isolated on a surface for doing good catalysis. But it's not so good for like keeping the shape of your nanoparticle the same, which helps our plasmon, as I'll actually show in the next slide. So these are some electron energy loss spectroscopy maps of those same gold nanocube plasmons. You can think of this measurement as being equivalent to turning on and off an electric field by the particles. Just like we talked about, this is another way of like exciting a plasmon. And then we can measure the response of the electrons in our sample to that electric field. And so the thing to note here are these plasmon hotspots that we can see visually depend on both geometry and particle arrangement. So especially in this image of the square, you can see that like if that was a sphere or an octahedra, there would certainly be hotspots in different locations, right? And so that tells you why if you had a copper cube that is going to start as a cube, but halfway through your catalysis, it's going to turn into something else. You lose those nice hotspots at the corners. It's less predictable. But we also see that this depends on particle arrangement. So 2 stacked particles or 3 stacked particles start to build up these really bright hotspots on the ends. And that's actually consistent through like a consistent principle of plasmon excitation is that the more sharp corners that you get close to each other, the brighter these hotspots get. And so that's something that I think about in this research is like, how can I tune the material, the shape, and the arrangement of the particles in my catalyst to have the best chance at degrading these PFAS molecules.
What's the difference between like B and C or K and L?
Yes, really good question. So these are different modes of the plasmon. And so a way to think about this is that like these started as the same data set. I only had one picture. And then I can do some post-processing to see, to separate out basically the different ways that the electrons oscillate. And so the way to think about this is like in the bulk metal that we started talking about when you set off your plasmon oscillator. You know, your electrons are moving around, but there's not a lot of constraints. You're in like a big, wide sea. It's metal as far as the eye can see. So you don't learn a lot about the different ways that a plasmon can exist. It's sort of just there in your big bulk metal. But when you're doing it in nanoparticles, and this is the reason that nanoparticles are, one of the reasons that nanoparticles are especially good for plasmonic catalysis. When you get smaller, you're like confining your plasmon. And so your electrons can bounce around in this direction and kind of build up on the edges, especially. But at the same time, they might also be bouncing around in this direction and building up on this face and building up on the face behind, or building up just on the corners, or building up on these edges. And so we can separate out those different plasmon modes in like post-processing and separate out and say, when we turn on and off our electric field, all of these things are happening simultaneously. We're getting electron buildup on these sides, on these sides, on these sides. And we can see, you know, that these corners are way stronger than anything else we see. So this arrangement, this geometry is really good for getting hotspots in those spots, even at the same time as there's, you know, some flat planes of activity.
So the black and white images on the left look like images. Are the ones on the colored ones on the right also direct images?
These colored ones were taken at the same time as these actual images. So we went pixel by pixel and collected like how much, you know, so these are like a transmission electron microscope. So you're shining an electron beam and you're measuring how much of it comes out the other side. And so all we're measuring with these pixels, you know, we measured here and we got 100% of the beam through. And we measured here and we got a lot less of the beam. We know something was in the way. But at the same time as we measured that pixel, we also turned on and off an electric field and measured the response in the electrons. And so then at the same time as we measured this pixel, we also measured this one and found some information about how the electrons responded.
So it almost looks like they're emitting something. An electromagnetic radiation, is that what's happening there?
Yeah, so this picture is a little complicated. I've tried to simplify it for the time frame, but yes, you can imagine when I talked about the plasma at the beginning, right? I'm saying electrons move, and then that causes the other electrons to move also, right? And one of the reasons that is that electrons are a charged particle. When you move a charged particle, you create electric and magnetic fields. And so what you are actually seeing here is the electric fields that are created by the movement of the electrons in the particle. And so, yes, they are like bright spots of electric field activity.
And you're sensing those how?
Yeah, so it's this electron energy loss spectroscopy. It's kind of all in the name. You can measure the amount of energy in the electron before you turn on and off this electric field.
Yeah.
And then you measure the energy afterwards. And the energy loss tells you about what that electron did in the meantime. And if what it did was like move around and set off some electric fields,
Yes.
you can trace that back.
So it's a constructed thing. It's not like emitting infrared light or.
No, you would not be able to see these. Yeah.
Okay, thank
We just make it look like that
you. Looks great.
for clarity's sake. Yeah, thank you. You kind of jumped the gun, everyone here. This is what I got. Thank you guys so much for listening. I have to acknowledge, I joke about being a self-made chemist, but the reality is that my coworkers in the Peidong Yang group made me a chemist. They taught me everything I know. I used all my support from Professor Peidong Yang, and thanks so much to you guys, Poppy the Science Puzzle, for having me here. And I will take other questions if you have them.
So you had with plasmon catalysts, and one of the things I got kind of nuts about was if you were replacing it, if you were handling it, you like got a dustpan, collected every bit of it you could, because an ounce was thousands of dollars. When using this in theory in applications for like PFAS and other water treatment settings, are there expectations that people might be able to recollect the material? Basically, the question here being, how much of this catalyst would you actually be able to recollect, reprocess, and reuse? And how much would maybe the expectation be once you've used it enough, it's just kind of lost?
Yeah, that's a good question. So I'll caveat this by saying we're at early stages. There's a reason I'm showing you my gold nanoparticles covered in copper and not palladium and platinum like I discussed. It's because we haven't gotten there yet. But my expectation would be that, one thing that you start looking at as you approach trying to scale up these kind of catalytic studies to industrial scale is the catalyst lifetime. And so that's one thing that tells you how much usage you're going to be going through. But also I've discussed like this wide picture of all these different metals that we could be using, many of which will host plasmons. And I'm talking about gold, which is an expensive metal, and then these even more expensive metals that might participate in PFAS. But a lot of people are thinking about how we can move away from noble metal catalysts into things that are cheaper. And so I think my expectation would be, this is the very bottom of that pyramid that ends with a usable product where you have to care about how expensive it is. And so, nobody has necessarily shown that you can use a plasmonic catalyst to do effective PFAS degradation. But if we can show that, maybe the next guy will figure out how to do it with cheaper materials or with a catalyst that lasts longer. A lot of people in my group that are working on some of the reactions that I mentioned that are a lot older and better studied are closer to that end of the process where they're starting to investigate, can we use cheaper stuff? Can we make these catalysts last a long time? I'm pretty far from that, but I'm optimistic. Someone could figure it out someday. Yeah.
Once we get past the how do we do this incredible technology question, what are the considerations so far on what happens after you break open a PFAS?
Yeah, so you can break PFAS molecules down into stuff that's pretty harmless, like these. The atoms that we're talking about are the regular ones. It's carbon, fluorine. These are hydrogen, oxygen, and carbon. So they are, at the end of the day, organic carbon-based molecules. So they're made of the same stuff as a lot of harmless things that we encounter every day. One thing that's interesting about this is that I talked today about PFAS, but there's another molecule that comes up a lot in these conversations, TFA, which is like, I think the story went that we like made all these PFAS molecules and we put them in everything, and then we're like, oh no, they're really bad. They build up in the human body and they give people cancer. Let's stop using them. And so then they just started using this other molecule called TFA, which is very similar, but it's shorter chain. So you could like chop off a bunch of those carbons and fluorines. And then it turns out that TFA is way worse for us and also harder to break down. But that's actually another molecule that I am studying in this same project. And so that one's like, maybe if your PFAS breaks down into TFA, that would be bad, right? But we want to go all the way, and all the bad stuff is in this carbon fluorine chain. And so the question is like, I keep talking about just breaking a bond. But really the key is to like break this carbon-fluorine bond and this one and that one, and keep breaking bonds on the same molecule until you've completely disassembled it. And we have to be able to do that because we have to get it from TFA back into like completely harmless components.
So what would be some of the practical uses be, and what would the practical usage be?
Yeah, that's a good question. So another part of the project that I didn't really have time to talk about, but I'll just give you the teaser. So these electron maps, we've talked about these enhanced electric field hotspots. And one thing that those allow you to do is to use another spectroscopic technique called Raman, which is like an inherently plasmon-based technique already, but you can do something called surface-enhanced Raman spectroscopy, where you use a plasmonic nanoparticle substrate. And what one thing that Raman spectroscopy or SIRS is really good for is low concentration detection of specific molecules like PFAS or TFA. And so the picture here is actually that we start by trying to quantify, measure the amount of PFAS or TFA in water. And so I'm like buying these chemicals and mixing them into water and trying to see how low of a concentration I can measure them at. And then you can try to break them down on the same catalyst surface. So I'm using these same gold nanoparticles decorated with whatever catalytic metal I measure. Then you really hit them with plasmons, try to break down the molecules. Then you can measure again the concentration. So in my mind, I'm like, at least that's a pretty straightforward workflow, right? Like built into it is our method for telling if we've done the job yet or not. Now, what does this look like in practicality for like taking a bunch of water and removing the PFAS from it? That's a little trickier. There's been some other phases of this project where we've talked about also an integrated scheme for enrichment. So if you know anything about metallic organic frameworks or covalent organic frameworks, these are really hip idea in chemistry recently. Professor Omar Yaghi at UC Berkeley won the Nobel Prize this year for his research on those materials. One thing that they do really well is they're sort of you can design a specific framework and then they have holes that are like perfectly PFAS shaped. And so they're really good for like collecting a bunch of PFAS and enriching it. And so maybe if you have these particles that could do detection and then degradation, you could wrap them in a sponge that absorbs PFAS out of the water, and then you don't need to like run a bunch of water through your catalyst. You can soak up a bunch of PFAS, degrade it, measure, see that you've done it successfully. So that would be like the very broad vision for a more functional system.
Going back to basically the mechanism of breakdown, what are the most common breakdown products that you can see when you've done this? Do you have a rough idea of like the distribution of products, and are some of those in any way like considered to be free radical products, or are they all strictly like positive, negative emission?
Yeah, that's a really good question that I don't have an answer to. This is you like when it's chemistry. If I haven't looked it up specifically, I can't usually puzzle out the answer. All I've got off the dome is that this chain is the bad part, and I don't really know where we go from there. But I could figure that out and get back to you.
When you're experimentally, like, let's say you want to take your images and you want different shaped gold nanoparticles, how do you edit the shape of something so small and invisible?
Yeah, so you don't have to do the editing. The way that we form these nanoparticles, so like these cubes that I'm working with, like I said, it's a colloidal synthesis process. So we're sort of mixing some metals together, and let's see if I can remember the way it really works. You're testing my chemistry again. Okay, so you have your metal atoms dissolved in solution, your metal ions. So in the case of gold, I've got like the gold juice, and it looks kind of yellow. And then I've got some kind of a reducing agent, which makes the electrons go a certain direction that I can't remember. But say that we're taking them away from the gold, and then that's going to make the gold want to form a lattice and turn into a solid metal. So once you mix together your gold juice and your reducing agent, you can start producing metal gold. It'll start appearing in your solution. But you want to control what kind of shape it turns into. And to do that, we use other molecules called ligands which are like a huge array of different molecules, but their function in colloidal synthesis is to constrain the growth of the nanoparticle. So they're going to attach to all of the new surfaces and limit the ways in which they can connect just because they're shaped the right way to block the growth here and to encourage the growth here. And so by changing which ligands you use, essentially, you can change which sort of shapes you grow. And so for me, I can pretty easily, like in almost identical batches, produce these gold cubes or gold octahedra or gold rhombic dodecahedra. But that's like the most, like I'm making the tiniest changes and I can already get those 3 different shapes. And tons of people have been doing tons of research on like, can you do 45 different steps and get the weirdest shape you've ever seen? So we have a ton of options to work from. I don't have to reinvent any chemistry to have like a whole suite of nanoparticle shapes to work from.
Is there then presumably like a range of radius on these things that's ideal?
Yeah, so that's a really good question. I've been thinking about that one. Well, you can imagine, I'm telling you all these cool things you can do with nanoparticles, but I don't always tell you like one is better than the other because I don't know. That's exactly the stage of research we're in, is like I have all of these opportunities to tune the catalyst that I'm using. And changing the shape of the nanoparticles is really easy to do. I was talking about this colloidal synthesis, but usually we do it in 2 stages. First, we make some seeds, which are like really small spherical nanoparticles. And then I can use those same seeds to make either cubes or octahedra or rhombic dodecahedra. And so the way to change the size is just by using more or less seeds with the same amount of gold juice. So the gold juice gets spread out evenly over all of the seeds, and then if there are less of them, then they end up bigger. So I basically have infinite tuning of the size of these nanoparticles in a certain range. And so these are 50 nanometer gold cubes just because that's what the guy before me was making. And when you change the nanoparticle shape, it also slightly changes that frequency that sets off the plasma oscillation. And so